In this lecture we'll study the binomial heap and a few other simple implementations of the priority queue. First of all, let's just remind ourselves what the priority queue is. The priority queue is an abstract data type. It's got the job of storing a collection of items. Say each item has a value v and an associated key or priority k. And we want to store a collection of these, and we want to be able to pick out the item with the smallest key. Obviously we have to be able to push new items. We'll specify the value and the key. And the main place we've used them in this course has been in Dijkstra's algorithm. Dijkstra's algorithm also needs the ability to take an existing item and decrease its key to a new lower key. In some cases we're interested in a few other methods. We might be interested in taking one priority queue and merging it with another. We may be interested in deleting a value. We may be interested in inspecting the item with the smallest key without removing it. I'm not going to look at those three. It's the first three methods that I really care about for now, for the purpose of Dijkstra's algorithm. So let's review some implementations of the priority queue. This is the first one we looked at, the binary heap. The defining feature of the binary heap, firstly there's the fact that it's a binary tree, almost complete. The other important property is the heap property. The heap property says that each element's key is required to be less than or equal to the keys of its children. So for example, here we see that 0 is smaller than 1 and 0 is smaller than 5 and so on, all the way down the tree. How does the binary heap implement those three key functions for the priority queue? Well, let's start with popmin. Popmin, first of all, extracts the root item. We always know that the root item is the smallest key in the entire heap by the heap property. So we first of all extract it. We need to fill in a new heap. So what we do is we take the very lastmost element in the heap, the one at the bottom. We swap that into the place of the root. Now this is no good anymore. It violates the heap property. 3, the new root, is larger than 1, its child, so we need to bubble down. We'll bubble down by swapping 3 and 1. Are we okay now? No, we're still violating the heap. 3 is larger than one of its children, so we still need to do some more bubbling down. And this is where we've ended up with a legitimate binary heap. Let's review what happens when we want to push a new item. We simply place the new item at the end. There's a problem here. This is no longer satisfies the heap property. Our new item is smaller than its parent, and the heap property says the parents have to be smaller than the children, so we need to bubble it up. Are we okay now? No, we're still not okay. This item is still smaller than its parent, so bubble up further. Is this okay? No, we still need to bubble up one more step, and we're done. Decrease key, very similar. You take arbitrary node, decrease its key, and then you bubble it up as far up the heap as necessary. All the operations that we've looked at so far are O of log n. Log n being simply the height of a binary tree. So let's move on to another implementation, the binomial heap. Before defining a binomial heap, I need to define a binomial tree. What is a binomial tree? Well, it's a particular type of tree with a certain shape. Here's an example of a tree with degree 0. A tree of degree 0 is a single node. If I take two binomial trees of degree 0 and merge them, then this is what is called a binomial tree of degree 1. If I take two binomial trees of degree 1 and I merge them, this is called a binomial tree of degree 2. If I take two binomial trees of degree 2 and merge them, what I end up with is called a binomial tree of degree 3. So let's just write out some properties that these binomial trees satisfy. In a binomial tree of degree k, the root has k children. That's just what we mean by degree. Degree of a node is the number of children it has. Next property, the tree has 2 to the k elements. The tree has height k. And just one more property, the children of the root are themselves binomial trees of degree k-1 and k-2 all the way down to 1 and 0. So this is just a bunch of facts about binomial trees. They're not very hard to prove, any of them. The proof of all of them is just by induction, and not a very interesting induction. So that's binomial trees. Now we can define what a binomial heap is. A binomial heap consists of a collection of binomial trees, each one a heap, and we're allowed at most one tree of each degree. So in this example we're looking at, we have one tree of degree 0, which contains 2 to the 0, i.e. one node, as we discussed on the previous slide, and we have one tree of degree 3, which has 2 to the 3 equals 8 nodes. There's an interesting property that comes out from this structure. The property is that the total number of nodes, in this case we've got 9 nodes in total, I can write that as 1 plus 8, corresponding to the binary representation. Let me write it out in binary in the following way. I'll write it as 1001, corresponding to binary digits. Leftmost digit, I'm going to call this the 1 digit, the 2 digit, the 4 digit, the 8 digit. So I've ended up writing my binary numbers back to front, just because by habit I write binomial trees back to front. I tend to write the smallest degree tree on the left and the largest degree tree on the right. But anyway, you can see that if you take the total number of nodes in the tree, write it out in binary, then the digits that we end up with tell us, does my binomial heap have a tree of size 1? Does it have a tree of size 2? Does it have a tree of size 4? Does it have a tree of size 8? And so on. So let's write that down as a general statement. In general, given a binomial heap with n items, the binary digits of n tell us which degree trees are present. And we can use that fact fairly straightforwardly to observe that the largest tree has degree, well, the precise value, log to the base 2 of n. It's pretty obvious that it's something to do with logarithm. It turns out to be the floor of the logarithm to base 2 of n, and there are less than or equal to floor of log to the base 2 of n plus 1 trees in total. Okay, so that's what a binomial heap is. Let's now review the operations on a binomial heap. Let's start off with, how do you push an item? You take the new item and you push it to the list of trees, and I've just pushed it to the front of the list. Now, the binomial heap does not let us have more than one tree of a given size. So next step is to merge trees of equal degree. Here we have a tree with key 4, which has degree 0, and a tree of key 3, which has degree 0. They can't coexist, so we have to merge them. and if we merge them, we end up with a tree of degree 1. This is the way we have to merge them. We need to merge them in such a way as to preserve the heap property, so I'll take the larger item 4 and make it a child of the smaller item 3. Great, so we've managed to create a new binomial heap after this operation. What's the cost of this? Cost is O of log n. Since we might have to repeat this merge process all the way up to the largest tree that there is, since there are O of log n trees, which might all be involved in the merge. That's only if we're unlucky. Typically, as in this case, you only need to touch a very small number of small trees in the merging. Okay, next operation. What happens if we decrease a key? Let's suppose I'll take this key 12 and I'll decrease it to 2. There's a problem here. It's a heap violator. It no longer satisfies the heap condition. I have to do something to fix up the heap condition. I'll do the same as we do in the binary heap. I'll take that node and I'll bubble it up. Hey presto, we're now in a situation where we do satisfy the heap condition. We're perfectly okay. 2 is smaller than its parent and larger than its child, so we're done. And what's the cost of this operation? Its cost is O of log n, the height of the tree that we're doing bubbling up inside. That's the largest number of operations that we might have to do. Bubble it up right from the bottom of the biggest tree up to the top of that tree. Next operation. Let's suppose we want to pop min. We want to take the smallest element in the entire heap and we want to remove it. So, first step is scan through all of the trees and look at their roots and ask which of these is smallest. In this case, 1 is smaller than 3, so this 1 is the node that we want to remove. We'll remove it. We're left with a bunch of children who no longer have their parents. What we do is we elevate those children to be on the root. We promote them. So the 1 has moved up to the root, the 6 has moved up to the root, and the 5 has moved up to the root. Okay, so first step, promote children. Second step, we need to fix up this binomial heap. The general rule of binomial heap is you are only allowed at one tree of a given degree. So we go through this process, merging trees of equal degree. Here I have 2 trees of degree 1, so I shall merge them. I'll merge them this way around. I'll make the 6 a child of the 3. I have to make the larger key a child of the smaller key because that's the way the heap property works. How are we done? No, we're not done yet because we still have 2 trees of degree 2. We're not allowed to have more than 1 tree of this given degree, so we have to merge them. And the way I'll merge them is, of course, I'll make 3 a child of 1 to satisfy the heap property, giving us a binomial heap again. What's the total amount of work we need to do? We need to do O of log n work to find the minimum item. We need to scan through each one of the trees and look at its root, and there are up to O of log n trees. Then we have to do O of log n work to promote the children. There are up to log n children, and each one of them needs to be put onto the root level, so that's O of log n work. And then what we have now, we had O of log n trees. We've added in potentially O of log n new trees, so now we have O of 2 log n, which is O of log n trees in total. The total amount of work that's needed to clean up all of those 2 log n trees is O of log n work to merge trees if necessary. So that's the binomial heap. Before we finish, it's just as well to think, this is quite an elaborate data structure. Do we really need any of this elaborateness? Let's look at a really simple implementation of a priority queue, a linked list implementation of a priority queue. All we're going to do is we're going to imagine we're going to store all the items as just a plain doubly linked list. I'll keep track of a pointer to the very first item in the list so that I can easily push a new item. And I also keep track of min item, a pointer to which one of these is the smallest. So what's the amount of work? What do the operations look like? If I want to push a new item, it's just really simple. I push a new item, I stick it on the front, I update my first pointer, and we're done. Oh, actually there's one other piece that needs to be done. Min item used to point to 1, I need to update min item, so I need to compare, is the new item smaller than the older min item? If so, I'll update min item. What's the amount of work involved in this? Push is O of 1. It's just a couple of pointers that we're working on, and also we can check very easily that the obvious way to implement decrease key is also O of 1. What does popmin look like? Let's suppose we want to pull out the smallest item, i.e. 1, i.e. the thing that min item points to. First of all, I'll slice it out of the list. But what we have to do now is we need to update min item. And the trouble is, with this data structure, we haven't got any structure to our data structure. We don't have anything to help us find what's the second smallest item in the list. So the only way to update min item is to scan through every single item in the list and ask, are you the smallest, are you the smallest, and so on. So this takes O of 1 work to take out the min item, but O of n work to scan for what the new item is. So what's our complexity of all of these algorithms we've looked at? We've looked at a binary heap where all the operations are O of log n. We looked at the binomial heap where all operations are log n. Again, it seems like it's not won us anything. It's actually got a benefit if we care about merging. Merging is O of log n, but it's O of n for a binary heap in the obvious implementation, which is left as an exercise. So the binomial heap, from the point of view of the operations that we're interested in so far, doesn't look any better than the binary heap. The linked list looks promising. It's got O of 1 for push and decrease key, but the price that we end up paying is that popmin is very expensive. What we'll look at in the next section is a much more advanced data structure, the Fibonacci heap, which achieves O of 1 cost for push and for decrease key, and O of log n for the popmin operation. There's also a little white lie going on here. In the binomial heap, it is true that the worst case cost of push is O of log n, but it is possible to show via an amortized analysis that the actual cost of pushing is O of 1 amortized. That's left as an example, and it's also part of the inspiration for the Fibonacci heap that we'll be looking at in the next lecture. Just before finishing, it's worth making a quick note about the implementation of a data structure like the binomial heap. When we're talking about the binomial heap, we said there are two things. There's the value and the key. The value, or the payload, that's the stuff that we're using the binomial heap to store. For example, if we're implementing Dijkstra's algorithm, we would want to store a number of properties at each vertex. We'd want to store a visited flag. We might want to store a flag saying, tell me the path that you use to reach this vertex, and so on. So in general, each node we've got a payload we want to store, and there's also a key that we want to store. And we'll imagine that there's a single node object which comprises both of these two things, plus a few other bits of information. It it's quite useful to keep track of what the degree of the node is, and in order to perform all the splicing, cutting, reinserting operations, it's useful to keep some pointers around. Let's say each node has a pointer to its parent, to a sibling, and to a child. And so if we see a binomial heap made up of 5 elements, this is actually how we'd implement it. Where there is no further child or no parent, I've just left the pointer fields blank. So this is how you might actually store one of these things as an object.